All right, so here's the scenario. I'm going to conduct a study. I'm going to gather a sample and ask a binomial question. How do I know how large my sample needs to be? How many do I need in my sample in order to make my margin of error whatever I want it to be? That's a calculation we can do. All right, so here's an example. Suppose, I don't know, I want to estimate the proportion of people in this town who prefer dogs to cats. So, okay, this is a binomial question. Everybody's going to give me a response that fits into one of two categories. Everyone's going to say dogs or cats, all right? So suppose my goal is I want to make a 90% confidence interval, and I want the margin of error on this confidence interval to be 2.5% or less. How big does the sample need to be? How many people do I need to talk to in order to make that happen? So this goes back to our margin of error for these type of confidence intervals. We know that for a one sample proportion confidence interval, the margin of error is z star, our critical z value, times the standard error, and that standard error is the square root of p hat times 1 minus p hat over n. Our goal here is we want to solve for n. So let's do a smidgen of algebra. Let's see, we take this expression. First, we divide both sides by z star. So now on the left-hand side, we have margin of error over z star equals the square root of p hat 1 minus p hat over n. Okay, good. I want to solve for n, so let's square both sides. And then let's see, I'm going to flip both sides, multiply both sides by p hat 1 minus p hat, and that will give me n equals p hat times 1 minus p hat times the quantity z star over the margin of error squared. Yay, we can still do algebra. Now let's look at this a little more carefully. Now, we have the margin of error, what we want that to be. We said we wanted our margin of error to be 2.5% or less. We can find z star. We said we wanted this to be a 90% confidence interval, so we can look up the critical z value. But what about p hat? We don't have that, and we won't have that until after we've done the study, so I need to plan in advance. I need to know how large my sample needs to be. So what do I do with p hat? What I do is I take a worst case scenario sort of thing. You see, the largest possible value, the largest possible number I can get out of p hat times quantity 1 minus p hat would be if p hat was exactly a half, was exactly 0.5. So what we're going to do is we're going to overestimate n by using 0.5 in both cases. 0.5 times 1 minus 0.5 is 0.25. And so here's our expression. The sample size we need is 0.25 times z star over the margin of error squared. All right, let's do this. We want to find z star, the critical z value. In this case, we want a 90% confidence interval. That means I want, in the normal distribution, I want 90% of it to be inside the interval, and then 10% to be outside of it. 5% above in the right tail, 5% below in the left tail. In order to find this corresponding critical z star value, I turn to R. I can get this from the qnorm command. I feed in the probability and see what comes out. Qnorm of 0.95 will give me 5% to the right, 95% to the left, and that gives me the exact same number. I could, as if I do negative Qnorm of 0.05. It's a symmetrical distribution. Both of them leave 5% in the tail, and so my critical z value is 1.64485. So let's put these numbers in and find the sample size. There's the 0.25. We have 1.64485 above. We have our margin of error. We want our margin of error to be no more than 2.5%, 0.025. We divide them, we square them, we equal them out, we do some multiplication. And what do we got? We have 1082.2. Except I'm surveying people. My sample size, whether it's people or tomato plants or whatever, my sample size n must be a whole number. And I want a sample size that will guarantee absolutely that our margin of error will be less than 0.025. So that's why we always, under all circumstances in this, we always round up. If I use a sample size of 1083, then I'm guaranteed that no matter what p hat is, my margin of error will be something less than 0.025. All right, so let's do it. Suppose we go out there, by some magic, we find a genuinely simple random sample of all the residents of the city. We ask 1,080 people, do you prefer dogs or cats? Suppose 671 of them prefer dogs. So then 671 divided by 1,083 gives us 0.62. So there's our point estimate, 62%. If I want to make a confidence interval, well, let's see. I need to do the standard error based on that. The square root of 0.62 times 1 minus 0.62 divided by 1083 gives us a standard error of 0.0147. We already looked up our critical z-star value. That's 1.64. We multiply these things together to get our margin of error. 1.64 times 0.0147 is 0.024. And note, that's less than the 2.5% error that we wanted. That was the whole goal. The point of these calculations is to get a margin of error less than 2.5%. And hooray, the methods we've learned here actually work. Shockingly enough, we got a margin of error less than 2.5%. Now we can actually put this into the confidence interval. So there's our 62% is plus or minus the 0.024. And that gives us our range. So we are 95% confident that between 59.6% and 64.4% of all the people, the whole population of all the people in our city, prefer dogs. So, quick summary. When gathering one sample of binomial data, we can calculate what our sample size must be in order to make sure that our confidence interval has a margin of error less than some value. In this case, we chose 2.5%. We use the confidence level to find the critical z-star value from Q norm. Then we use that lovely magical formula that n equals 0.25 times quantity z-star over the margin of error squared. When we get the results, we always round up so that we will be guaranteed that in the end, our margin of error will be smaller than whatever we chose.